Welcome to the solutions to the Regents Physics Spring and Simple Harmonic Motion problem set. Problems numbers 5 through 9. Let's go ahead and get started. We got number 5. Does the period of a pendulum depend on the mass of the bob, length of the string? Upon what else does the period of the pendulum depend? So starting off with a conceptual question here. To answer this, we go ahead and start with the period for a pendulum. T equals 2 pi square root of L over G. And we note that the length of the pendulum is the dependent variable in the numerator of the fraction. And the constant here is the acceleration due to gravity. So go ahead and answer our questions. Does the period of the pendulum depend on the mass of the bob? The answer is no. It's independent of mass. Doesn't matter how much mass is attached to the bottom of the pendulum. It doesn't show up anywhere in the period formula. Length of the string, yes, that's the dependent variable. And upon what else does the period of a pendulum depend? And the answer to that is acceleration due to gravity. Now, near the surface of the Earth, the acceleration due to gravity is constant, but that can change if you change the location. Say, now take your pendulum to the moon, for example, you will end up with a different period because you have a different value of little g. But that value, little g, remains constant near the surface of the moon. So it's still at a constant value, just that it can change depending on location. One other thing to note in this is kind of important, is that the period also depends on the angle from the vertical with which the pendulum swings. As long as that angle is 10 degrees or less, the period of the pendulum will remain constant. When you get out beyond 10 degrees, there are other components of forces that that also impact the period of the pendulum. We don't worry about those in this course, so you just need to understand that the period of the pendulum remains constant with an angle from the vertical that is 10 degrees or less. Number 6, does the period of a mass on an oscillating spring depend on the mass attached to the spring? The stretch, compression, amplitude of the spring. Upon what else does the period of an oscillating spring depend? This is a typo here. This would be period of an oscillating spring. Well, again, we start with the period formula for an oscillating spring, and that would be T equals 2 pi square root of M over K. And we have our dependent variable in the numerator here is the mass, and our constant in the denominator is the spring constant. Let's go ahead and answer the questions. Does the period of a mass on an oscillating spring depend on the mass attached to the spring? The answer is yes. That's the dependent variable. The stretch, compression, amplitude of the spring, that would be X. We don't see that anywhere here, so the answer is no. It does not depend on that. And upon what else does the period of an oscillating spring depend? It depends on the spring constant of the spring, which of course is individual to each spring itself. Number 7, can a pendulum clock be used in the orbiting International Space Station? And explain. Well, starting with our equation for the period of a pendulum, which would be in the pendulum clock, T equals 2 pi square root of L over G. Well, the key to this answer is the fact that the International Space Station orbiting the Earth is in a constant state of free fall. If you've ever seen video of the occupants inside the International Space Station, you see them floating around. They look like they're weightless. And the reason for that is because the International Space Station, while it's orbiting the Earth, is constantly falling back towards Earth while it maintains its orbit. Because of this, the apparent acceleration due to gravity on the International Space Station is 0. That's why the astronauts and the contents appear to be weightless, because they don't experience acceleration due to gravity. This would be the same concept as we discussed earlier this year as being an elevator and somebody cutting the cable. Well, you would be free falling along with the elevator, so a scale underneath your feet would read 0. 0 acceleration due to gravity as a result of that. So there would be, this would not be advisable. Can a pendulum clock be used in orbiting International Space Station? The answer is no, because the acceleration due to gravity and the International Space Station would appear to be 0. Neat question to think about. Number 8, how long must the pendulum be to have a period of 1 second on the Earth? Well, we're going to start with our period of a pendulum formula. T equals 2 pi square root of L over G. In our substitution, we want our period to be 1 second in length, equals 2 pi square root L over 9.81 meters per second squared. We just have to solve this algebraically for L. To accomplish that, we take our 1 second, we divide by 2 pi, we square both sides to get rid of the square root, and then multiply by 9.81. Doing that and solving for L, we get a value of 0.253 meters. And just for reference sake, that's 25 centimeters. So, if you're ever in a scenario where you are needing some kind of timing device or a way to keep time, you can quickly make a 1 second clock by taking a 25 centimeter, that's a quarter of a meter, length of string, attaching an object to it, and then fixing it to a pivot point and putting it in oscillation of 10 degrees or less from the vertical, and your total period of swing over and back would be 1 second. Number 9, how much mass must be attached to a spring of spring constant 10 newtons per meter so that its period of oscillation is 1 second? Well, similarly, we're going to start with the period of an oscillating spring, which is T equals 2 pi square root M over K. We want our period to once again be 1 second, and 2 pi square root of M over our spring constant, which is 10.0 newtons per meter. Again, we would take our 1 second, divide by 2 pi, square both sides to get rid of the square root, and then multiply by 10, and we would get a mass value of 0.253 kilograms. For reference, because you've worked with the masses here in the lab, that'd be 253 grams, which you're pretty familiar with, approximately how much that is. All right, that'll do it for our introduction to simple harmonic motion and the questions here that you've had. More to come as we do number 10 in class tomorrow.